Hello. Today I want to talk about part 7 of my series, Essential Theorems for Harmonic Astrology. So, let me share my screen and we'll get started. As usual, this takes just a minute. Gotta get rid of panels so I can see what I'm doing. Almost there. Okay, I'm ready. Essential Theorems for Harmonic Astrology, part 7, the harmonic K equal to M times N. Now, the next theorem we want to look at shows that if K is equal to M times N, where M and N are natural numbers, then the K harmonic is equal to the M harmonic of the N harmonic. For example, the 6 harmonic chart is identical to the 3 harmonic of the 2 harmonic chart, and similarly, the 6 harmonic chart is identical to the 2 harmonic chart of the 3 harmonic chart. This relationship also always holds for natural numbers, but not always for other kinds of rational number harmonics. To prove this, we'll begin with a simple lemma. So, lemma 1, if n is a natural number and q and p are positive rational numbers, then n times q modulo p, this whole thing evaluated modulo p, is just equal to n times q modulo p. In other words, rather than having to reduce possibly q first by modulo p, you can just go ahead and multiply n times q and reduce the end result modulo p. Now, this is kind of a general lemma, but specifically, we'll usually just have p equal to 360 degrees. So every time you see a p down here, you could just think in your head that what we're doing is reducing something modulo 360 degrees. So let's suppose that r is the remainder after dividing q by p. Then q is going to be equal to w times p plus r, where w is a whole number. And it follows that q modulo p is just equal to r. That's because when you reduce q modulo p, this part here, which is just a whole number multiple of p, it's going to have remainder 0 when you divide it by p. And the only thing you're going to be left with in terms of a remainder is going to be r. Okay, so from this it follows this q modulo p equal r. From that it follows that n times q modulo p is equal to just n times r, because q modulo p is equal to r. Also, n times q is equal to n times parentheses w times p plus r. We get that from up here. Distribute the n across the sum, and this is equal to n times w times p plus n times r. Hence, if I take n times q modulo p, that is going to be the same as, let's see, this expression here, evaluated modulo p. However, since n times w times p is a whole number multiple of p, it's not going to contribute anything to the remainder that we get when we reduce this modulo p, when you divide this thing by p. So it follows that n times q modulo p, which is equal to n times w times p plus nr modulo p, that can just be reduced to n times r modulo p. So therefore, what do we have here? We have that n times q modulo p in parentheses, and then that whole thing, evaluated modulo p. Well, this thing is equal to r, so this is equal to n times r modulo p, but we just saw that n times r modulo p is equal to n times q modulo p. and showing that this is equal to this. That's what we want to do. So we have proven this lemma. Now again, I'll note that lemma 1 will usually be applied to the case where P is equal to 360 degrees. Thus, in other words, I will use the conditions of lemma 1 to conclude that for a natural number n and a positive rational number q, that n times parentheses q modulo 360 degrees parentheses close, and then this whole thing evaluated modulo 360 degrees is just equal to n times q, that result evaluated modulo 360 degrees. And here I do a concrete example. I did this on my calculator, so I just showed these decimal expansions to however far out they went on my calculator. So that may be exact, maybe just kind of an approximation. But anyway, let's suppose that n is 100, q equal to 1,260 divided by 3.1. That'll be a positive rational number, and p is equal to 360 degrees. Then n times parentheses q modulo 360, the whole thing modulo 360, that's 100 times this rational number, modulo 360 degrees, and then the whole thing evaluated modulo 360 degrees. Doing this on my calculator, I get about 46.4516129. Multiply that by 100, evaluated modulo 360 degrees. And when I multiply by 100, I get this, evaluated modulo 360 degrees. That comes out to about 325.16129 degrees. On the other hand, if I evaluate n times q and then reduce modulo 360 degrees just once, that's 100 times 1,260 over 3.1, reduce modulo 360 degrees. This product comes out to 40,645.16129, evaluated modulo 360 degrees, and sure enough, I get the same thing I got up here, 325.16129 degrees. So, at least in that example, the result of the lemma works. Okay. Now, Theorem 6. Given any angle such that 0 degrees less than or equal to theta less than 360 degrees, and any natural number k equal to m times n, where m and n are also natural numbers, then the k harmonic chart is identical to the m harmonic chart of the n harmonic chart. Well, let's take a look at the proof. Okay, recall that to convert a natal angle theta was 0 degrees less than or equal to theta less than 360 degrees to its corresponding angle in the k, m, or n harmonic charts for natural numbers k, m, or n respectively, we only need to multiply our angle theta by k, m, or n and express the result modulo 360 degrees. But by lemma 1, what do we have? We have that k times theta modulo 360 degrees is equal to m times n times theta modulo 360 degrees. But here's where lemma 1 comes into play. That is equal to m times parentheses n times theta modulo 360 degrees, parentheses close, and brackets close, this whole thing, evaluated modulo 360 degrees. But this last expression is the m harmonic of the n harmonic, and so it has been shown that if k is equal to m times n, where m and n are natural numbers, then the k harmonic is equal to the m harmonic of the n harmonic. So this is how you would evaluate the k harmonic for this angle theta. Just multiply it by k, reduce the result modulo theta. But here we showed you can do it in stages. You could first convert theta to the n harmonic. That's what this expression parentheses does. And then you convert that result to the M harmonic. That's what the rest of it does. Okay, so we proved the theorem. I have a corollary here. Given any angle theta, such as 0 degrees less than or equal to theta, less than 360 degrees, and any natural number k equal to m times n, where m and n are also natural numbers, then the m harmonic chart of the n harmonic is equal to the n harmonic of the m harmonic. And this just follows immediately from Theorem 6, since both are equal to the k harmonic. So you can write k as either m times n, or switch the order, n times m. And you just go through the same proof, and you get the result that the m harmonic of the n harmonic is the same as the n harmonic of the m harmonic. They're both equal to the k harmonic, so they're equal to each other. Okay, notice that while Theorem 6 and Corollary 6.1 hold true for all natural number harmonics, they don't hold true for all positive rational number harmonics. An example of this is if I take 2.3 times, and then in parentheses, I have 1.3 times 330 degrees modulo 360 degrees. Take this whole thing, reduce it, modulo 360 degrees. I wind up with 158.7 degrees. But if I take 1.3 times parentheses 2.3 times 330 degrees modulo 360 degrees, and reduce that whole thing modulo 360 degrees, it should come out to something different, 50.7 degrees. So here, 2.3 and 1.3, they're my m and n, except that they're not, m and n are not natural numbers now. They're positive rational numbers that are not natural numbers. And this shows that the order in which you do things now makes a difference. This harmonic of this harmonic is not the same as the opposite order, this harmonic times this harmonic. Okay, that is going to be it. So I'll stop sharing my screen. And I'm back. So that is part 7 of this series. I hope you join me again for part 8. But for now, I'll just say so long and be well.